Hello, and welcome to Lesson 3.1. So, today's lesson, we're going to launch Chapter 3 off with studying radicals. And you may ask, what's a radical? Well, it's the symbol that we often think of as a square root symbol. It's anything that we go to do this with. So, like, for instance, this. This is a radical expression. Um, there can be other things written here, but it's understood to be a 2. It's understood to be a square root. All we're going to look at in this lesson are square roots and cube roots, but we could go bigger to fourth roots or fifth roots or sixth roots, but I could put any number I want there. If there's nothing there, this is one of the few places in algebra where it's not understood to be a 1, it's understood to be a 2. So if I erase that out of there, it's understood to be a 2, a square root. Now, let's just start with square roots, and a good question is, what is a square root? Well, one understanding of it, or one simple way to explain it, not a textbook way to explain it, but how we talk, just a human interaction way, would be like it's kind of like the opposite of squaring something, opposite of an exponent of 2. So what does it mean to square something? Well, that's like if I take the number 3 and I square it, that means I'm multiplying it by itself twice, and that would give me 9. So squaring something means any exponent is counting how many of these bases I have, and a square just means an exponent of 2. So if I have 3 squared, I want to go 3 times 3 equals 9. Well, in algebra, if you have not realized this yet, every time we teach you a skill, we teach you how to go backwards and undo a skill. And so that's what these radicals or these roots are going to do. We're going to start with a number like this and say, oh, the square root of 9. Well, what we're asking, I'm going to be really annoying and show steps you don't usually, is are there two things that multiply to give us 9? Or let me rephrase that. Is there something that I can multiply twice to get 9? And you know that 9 is 3 times 3. Well, what a square root says is, oh, okay, well, it undoes the squaring. So if it's 3 and 3, that's the same thing. So I could write 9 as 3 squared, right? And then if I have 3 squared, what a square root does is it undoes the squared, right? It's the opposite of a squared. The square root of a squared thing is the plain base there. So it's 3. Now you know this. We will not show any of that white work unless we just need to, what I have written in white, unless we really need to think through this. We will just say, okay, what's the square root of 9? And you say, okay, is there something that multiplies by itself to give you 9? Yes, that would be 3. So we go much faster with square roots, right? Now, for fun, though, we can expand this idea and not just do numbers. We could even, as any good bit of algebra will involve, throw in some variables. So I could ask you for something like the square root of x to the 6th power. Well, that's really interesting. But once again, we're going to say, are there any two things that could multiply? Can I break something up like this? And you could say, oh, anything multiplied by itself that'd give me x to the 6. And if you know your exponent rules, if you don't know your exponent rules, go back to the introduction lesson. Well, it's a bunch of videos from Math 105, the previous one. I've included those videos for lesson 1.1 to go over your exponent rules. But x to the third times x to the third would give us x to the 6, because the exponent rule says if you're multiplying like bases, you add the exponents. So then what that means is I could write it, like I said, this is not usually what we show, but I could write it as x to the third squared, and my square root and square will undo each other, and I will have x to the third. Typically, we're not going to stress over showing all this work. What we'll just do is say, hey, x to the 6, is there anything times itself that gives you x to the 6? And you'll say, yeah, x to the third. Now, this is next time's lesson, but one thing that I do is, since this is a square root, it's literally just halving these exponents inside here. Notice I went from a 6 to a 3. We could do one more just to see if you feel comfortable with that idea. Let's see. Let's go with a y to the 8th power. And if we were to take all of our time to show all this thinking, is there anything times itself that gives you y to the eighth? And yeah, that would be y to the fourth times y to the fourth. And so if I was being really, really extra here and showing every bit of thinking my brain is processing, I could show that before jumping to the answer as, oh, y to the fourth is the square root of y to the eighth. Or, once again, notice that it just halves this exponent. To square root something means to half it. We'll get into why that is. I'll explain that in next lesson. Although this would be a good spot, but maybe I'll just leave it as a tease to explain why this just halves that. Okay? So this means we can get into kind of some bigger and more difficult things. I could start mixing letters and numbers together. So I could do something like this, 9x to the 10th. Well, we kind of need, we don't really, but we kind of need a property which I'll teach you here in a few minutes. Oh, actually, that's in the next lesson too. Oh, next lesson's a good one. It has good stuff in it. Look at this. What by itself would multiply to give me 9x to the 10th? And I'm going to show these extra steps. Well, that would be 3x to the 5th. If you took the time and you knew your exponent rules really well to multiply these back together, that would give you 9x to the 10th, because the 3 times the 3 is 9, x to the 10th. X to the 5th, x to the 5th would be x to the 10th. And so that is 3x to the 5th squared, and a square root undoes the squared, and so this is 3x to the 5th. I don't want you thinking this, well, I want you to think, but I don't want you struggling this hard over this. If I have variables and I have numbers, I can kind of handle them separately. What's the square root of 9? We know that's 3. What's the square root of x to the 10th? Well, we're just going to half the 10, so that'll be x to the 5. Okay, that wasn't really that difficult. Yes, this is the reason why it's 3x to the 5th, this line of thinking, but hopefully you can get cozy with jumping faster through these. Now, we do need to discuss something about negatives. Is there a difference? Well, later in the course we'll be able to handle this better. But let's touch on just a little bit of this now. Square root of a negative square root of 36 versus square root of negative 36. Can I do either of these, both of these, one of these? And the answer is, I can only do one of them. Okay? So for instance, let's look at this one. This negative is just on the outside of this radical symbol. I don't know why I'm writing it twice. Let me, I could add parentheses. I'm not going to usually do that, but that negative is on the outside. It is not messing with the radical at all. So I can do the square root of 36 is 6. So negative square root of 36 is negative 6. This negative just floats out front for the ride. Over here now, think very carefully. What number times itself will give you a negative 36? And hopefully, you might pause and take some time to think about this, but if you think about it, there is no real number that will do that for us. Think about all the real numbers, because if I take a positive number, a positive times a positive is a positive. If I take a negative number, a negative times a negative is a positive. If I have to take the same number and multiply it by itself, I'm always going to get a positive. Therefore, I don't have a way of handling that right now at this point in the course. Later in the course, we'll have a way to handle this. Man, this lesson is filled with a bunch of teasers for later. But later in the course, we'll be able to handle this, okay? Not right now, though. So right now, we're going to say no real numbers can do that. So no real solution or no real numbers. Okay? So square roots, not that hard. You just think of something multiplied by itself, which will give you this thing. So 6 times 6 is 36, so that's the square root of it. We can handle letters or variables with our numbers. Remember, square roots are just basically halving this exponent. And there's the reasoning for it. So that wasn't too hard. Let's dive into now cube roots. We just did square roots. Let's do cube roots. And once again, a good question is, what's a cube root? Well, it's kind of the opposite of a third power, okay, of a cube. For instance, let's see. If I ask you to find the cube root of 8, 8 is a perfect cube root. The reason 8 is a perfect cube root is I'm looking for something times itself 3 times. So I can write 8 as 2 times 2 times 2. So the same number 3 times would give me 8. Well, that is the same thing you would agree as a 2 to the third power, right? 2 times 2 times 2 is 2 to the third. Oh, well, a third root, or a cube root as we call it, undoes a cube, or a third power. So this is just 2. So the cube root of 8 is just 2. Oh, well, that's not so bad. I'm just looking for something that I can think of that would be multiplied by itself with 3 of them there to give me back this number. So we could go with a little bit of a harder number. Still doing just cubed roots. What if I ask for 64? Is there a number times itself with 3 of them there that would give us 64? And what you may want to do is you may want to kind of start to learn or have these written down, perfect cube roots out to a certain number. So to the third, to the third, to the third, to the third. What are these? 2 to the third is 8. 3 to the third is 27. 4 to the third is 64. 5 to the third is 125. So you may want to, and you could easily do this by just taking a calculator and trying, or just, you know, oh, I did 5 to the third. How about 6 to the third? Where's my exponent button? I think that's my exponent. 6 to the third is 216. So we can add another one. 6 to the third is 216. Okay. So we can keep adding other things to this if you wanted to. 7 to the third. This is once again the Desmos calculator, which is free online, which is a good calculator for you to use. 7 to the third. So we could get all the perfect 343. So we could get all the perfect cubes over here. What was that? 343? All right. So 64, is there any of this perfect cube? Oh yeah, 64. What's the base? 4. So this is the same thing as 4 to the third. And a cube root and a cube cancel. This is just a 4. You don't need to show this middle step. You should be able to jump there. Now, I can handle numbers then. Can I handle variables with exponents? So let's look at the cube root of x to the 6th. We did x to the 6th with a square root. Can I also do x to the 6th as a cube root? And the answer is yes. Because, is there something I could write out times itself 3 times? Yeah, x squared times x squared times x squared. Exponent rules tell you add these, that would give us back 6. Yes. So this is, in fact, a perfect cube. It happens to be x squared to the third power, because there's 3 of these. Oh, then this third root and this third power would cancel, and this is x squared. Can we find a pattern like last time? With the square roots, we halved these exponents. What am I doing with the exponents when I'm taking a cube root? Notice I'm dividing by 3, or cutting it into a third. So what's a third of 6? 2. So then I can once again do third roots that are bigger and better. Like I can go 27x to the 12th power. And you should be able to easily tell me what the answer is. Well, if you don't know that 27 is a perfect cube root, I would keep a list of perfect cube roots handy, and perfect square roots will help with the others too. 27 is a perfect cube root. That is 3 to the third power. I don't know why I'm writing the radical down again. We can go ahead and jump to the answer. So that is 3. And x to the 12th power, well, let's just third the exponent. So 12 divided by 3 is 4. So that'd be x to the 4th. Okay, now if you don't agree with that or you're not sure, we can do some scratch work to make sure, this scratch thinking. I'll go ahead and tell you. 3x to the 4th times 3x to the 4th times 3x to the fourth. If you were to multiply that back out, 3 times 3 times 3 is 27. X to the fourth times x to the fourth times x to the fourth is x to the 12th. So I could write this as the third root, or the cube root, of 3x to the fourth to the third power, because there's 3 of these 3x to the fourth. Oh, the third root, the third power cancel, and I have 3x to the fourth. So we can handle pretty complex things. Okay, so this is, I want you to feel pretty cozy. You know, you have some homework to try this, the square roots and the cube roots. There is one other thing I want to consider. With a cube root, I have different abilities with the negatives. So for instance, if I were to go with, well, we just did 27, but if I go with a cube root of negative 27, well, with a square root, I'd be stuck. But with a cube root, if you think about this, I'm going to take the time to write it all out. Negative 3 times negative 3 times negative 3, that would give me negative 27. A negative times a negative is a positive, and a positive times a negative is a negative. So I can do negatives. I'm just going to, when I do third roots, I'm going to end up keeping the same sign. And so that would be negative 3 is your answer. So it's okay to do these with third roots. With square roots, I can't do these negatives. Okay. Now, there's one last kind of thing we want to get to, and that's to be able to graph these things. Okay, to be able to graph them. So we're going to graph square root functions and cube root functions. Now, the best way to do this is just to make a table of values. We're going to use a table of x's and y's, or inputs and outputs, however you want to think of it. So let me give you an example. We're going to go not too crazy. We're going to go with what are called like shifted parent functions. What that means is they're not going to be insanely weird. So let's look at a square root function, x minus 4. If I want to graph this thing, what we're going to do is we're going to pick some x values, find the outputs, and then we'll just plot our points, our x and y pairs or outputs here. Now, I'll go ahead and tell you, if we're looking at this thing in here, if we're looking at x minus 4 square rooted, it's going to work a lot better, or we're going to get whole numbers. We only want to graph with whole numbers if what we have on the inside is a perfect square. Whoops, I missed a letter. Perfect square. It'll be much better if we do that. So we're going to pick x's. I guess it doesn't matter. You can pick x's all day long, but we're not going to graph decimals. We're only going to graph whole numbers. So for instance, I have to be careful here. If I try, draw a line here, so this is our scratch work over here. If I try picking x as 0, and I plug 0 in, let's see, if I let x be 0, well, what's 0 minus 4? That's negative 4. Can I take the square root of a negative? Ah, no. That's undefined for us right now, or not a real number. So we don't want to use x equals 0. We could try 1, that'd be negative as well. If I put a 2 in, that'd be a 3. What's the first number that I can plug in for x that would give me something that's not negative? Oh yeah, if I put a 4 in there, let's try that. Let's plug a 4 in. 4 minus 4 equals 0. What's the square root of 0? Oh yeah, it's just 0. Okay, we got our first point. So I'll suggest, let me go ahead and give you this tip. Whenever you're using square root functions, or you're graphing square root functions, my first x I try to start with is a one that gives me a 0 in here. Okay, a 0 on the inside. That's a good starting place. Okay, a good place to start. Now, I want to pick things from there. Usually, depending on what's happening with your equation, you can usually try the very next number, like 5. Let's try. Let's give it a try. 5 minus 4, that equals 1. Do you know what the square root of 1 is? It is 1, because 1 times 1 is 1. Okay, that's not too bad. So there we go. Now, what happens if I just keep trying numbers? Let's try the next number. Let's try a 6. A 6. So square root of 6 minus 4. Ooh, that's 2. That's a nasty decimal. I don't want to use decimals, and so I don't want to use 6. So you can keep picking numbers, 7, 8, 9, 10. But what's going to make this, like I said up here, like I wrote in green, what's going to make this look much prettier, be much easier, is if I pick x values to make this a perfect square. And so it's useful to know the perfect squares. 16, 25, just like I told you last page of notes, to know the perfect cubes, it's very useful to know perfect squares. So let's see, I got 0 and 1. Let's see about getting a 4. What would I need to subtract? What would I need to put here to make this a 4? Oh, 8. 8 minus 4. So 8 should be a good choice. 8 minus 4 is 4. What's the square root of 4? It's 2. Okay. Maybe one more would be enough. So I want to make it 9. If I'm going to subtract 4 from it, what's 4 more than 9? Oh, maybe 13. Let's try 13. 13 minus 4 is 9, and the square root of 9 is 3. Nice. Okay. And so now I have these 4 points that I would like to try to graph. Okay. What I may do here, so I can see nicely, is let me minimize all this work, get it out the way. If you need to look at it, you can rewind it and pause. We'll shrink it down. Let me get a piece of graph paper really quickly. And let's see. There's a nice piece. Oop. We'll move this more out of the way. We'll just tuck it down there. There we go. There we go. Okay. All right. Let's see. That kind of looks weird, so I hope that you can see my graph. I might be able to change the background color of it. Oh, I can make those stand out. There we go. That's better. Making those stand out a little more. All right. So I'm going to plot these points. So the point 4, 0. So that's our x, y. So 0 or 4 in the x direction. 1, 2, 3, 4. And 0 in the height. So there's a point. The point 5, 1. So 1, 2, 3, 4, 5, 1. The point 8, 2. So let's see. This was 4, 5, 6, 7, 8. 1, 2. Oh, and I can't quite fit this one, but let's kind of imagine where 13, 3 would be. So this is, let's see, that's 8, 9, 10, 11, 12, 13, and 3 would be about, so it'd be about right there, right? So when I go to draw this, this is an interesting shape. Does anybody happen to know what this shape is? Some teachers call this like a shooting star, but what it is basically half of a parabola. There's the other half. Don't draw the other half. We're just drawing this half. But all these square root functions, anytime I ask you to graph a square root function, it's going to look like this, like a little, I need to curve it more. I did a horrible job trying to curve it, but it's half of a parabola. Okay, and you need to get at least 3 points, to be able to graph this thing. I will go ahead and tell you, while I do want you knowing how to graph by hand, Desmos has a graphing calculator as well, and you could easily put these things in. Instead of function notation, I'll use y equals, let's see, sqrt gives you a square root. And what was it, x minus 4? There. And that's the same beautiful graph we had. There's our point x2, our point 5, 1, our point 4, 0. So there's our beautiful graph. Use Desmos if you need to kind of help you visualize the graphs better. Now, back to one more example, then I'll be done. Let me grab this, copy, paste. All right, one more. So we've done square roots. We'd also like to be able to graph cube roots. So let's do something like this. Let's go with a function, and we'll do it this way. We'll go with a cube root of x. Outside of the cube root, we'll go plus 2. So we'd like to be able to graph this. Now, once again, we're going to make a table, and you're going to pick the x's. You can pick any x's you want, but only some of them are going to be nice. Now, once again, it might be nice to know perfect cubes. We would like to have perfect cubes plugged in here. So perfect cubes, let's see, 1 is a perfect cube. Well, actually, 0 we could say is a perfect cube. 1 is a perfect cube. 8 is a perfect cube. 27 is a perfect cube. That's probably big enough. We don't want to get too much bigger than that. So if I plug in a 0, let's see what we get. So if I put a 0 in here, plus 2, let's see, the cube root of 0 is 0, and 0 plus 2 is 2, so that worked out nicely. If I put a 1 in there, I guess I should change colors so that it looks nicer. So if I put a 1 in there, let's put a 1 in there. Let's plug a 1 in. So cube root of 1 plus 2. Let's see, cube root of 1 is 1. 1 plus 2 is 3. Okay, well that's easy. What if I put an 8 in there? Plug an 8 in. So the cube root of 8 plus 2. Cube root of 8 would be 2. So 2 plus 2 is 4. Okay. Ooh, wait a second. So these are perfect cubes. I don't want to put in 27. I can't count to 27. My graph's not big enough. I could also do the negative of these. Well, there's no such thing as negative 0, but I could do negative 1 and negative 8. Let's try those as well. So negative 1. Oh, let's change colors. Purple. Negative 1. So if I take the cube root of negative 1. Now, I cannot do this with a square root. Cube root of negative 1 is negative 1. And negative 1 plus 2 is 1. Okay? And then let's just add on one last one. We will go with negative 8. So if I do the cube root of negative 8 plus 2, that will be negative 2 plus 2. That will be 0. Okay, so I got some points to graph here. Let's go ahead and graph negative 8, 0. 2, 3, 4, 5, 6, 7, 8. Negative 8, 0. Negative 1, 1. Negative 1, 1. Let's do, I'll put them in the same color as they're worked in. Negative 1, 1. 8, 4. 8. 1, 2, 3, 4. Oh, I can't count. That's 3. 4. All right, let's see. 1, 3. Where's blue? 1, 1, 2, 3. And 0, 2. 0, 1, 2. And this looks like an, oh, I didn't change colors for that one. I guess red was technically. All right, and this looks like a really interesting graph. What it is it's kind of like a squiggle. It's got like almost like a weird elongated S. Okay? It looks just like that. Well, that's the best I can graph it. So whenever you graph these, you're going to probably want to try to get 5 points, 2 on each side of the middle of the squiggle, the inflection point of this graph. Now, help me remember this. Square cube root of x to the... If I wanted to graph this in my Desmos graphing calculator, I wonder how Desmos does cube roots. I bet I can do, well, I know I can do it this way. I can go x, we'll talk about this next lesson, but I can say to the 1/3 power, and then plus 2, boom, there's our beautiful graph. There's my 2, 0 point. Our, where was it at? 1, 3 point, 8, 4. So there's the beautiful same graph. Well, that's all I have for you. So you have a few skills here, just really 4 skills. Be able to take square roots, especially of something like, where was it at? Like this, 9x 10th. Be able to take cube roots, especially of something like 27x to the 4th. And be able to graph both. Be able to graph a square root and be able to graph a cube root. So that's all you need for today's lesson. All right? Well, I'll turn you loose if you try the homework, and if you have any questions, just send me an email. I'll see you next time.